Okay, thank you very much. And thank you very much for having me here and letting me share our work on periodically driven systems that we study with ultracold atoms in order to engineer topological physics or topological band structures. So as was briefly mentioned, I will discuss how we engineer these model systems in order to study topological phases. And our work is of course mainly inspired by all of these beautiful materials and phenomena that have been found in solid state systems. In particular, the very early works on integer and fractional quantum Hall insulators, where we believe there's still enough and many open questions that we could try to address in our cold atom systems. And I'm not trying to give an overview here because there will be many other talks discussing various aspects of these interesting materials in 2D and 3D. And we've also heard that there will be a talk about wild materials as well. So we are trying to develop techniques in order to emulate these types of phenomena in cold atom systems, but also try to see how these techniques can actually be used in order to go beyond what we already know and engineer systems that have topological properties that are new and genuinely out of equilibrium, as we will see with the technique that we are using here, which is periodic driving. So I will briefly introduce the technique and explain how we use it in order to engineer these what we call anomalous Floquet systems, which show topological properties that go beyond what we know from static systems. And then I will go more into the experimental side and explain how we can actually probe topological phase transitions points, how we can identify and how we can characterize their topological properties. So just very, very briefly how our system looks like. As I mentioned, we work with cold atoms, in particular in optical lattices, and most of the time we work in regimes that are well described by tight binding Hamiltonians. So we realize in our case, since we work with bosonic atoms, the Bose-Hubbard model, which is characterized by this hopping matrix element J, and the interaction energy U if the particles sit on the same side. Now, for the experiments that I'm going to discuss here, the interaction energy is tuned to extremely small values, so we can safely neglect it and consider it as a single particle system where we have only the kinetic energy term. And moreover, we start all our experiments by preparing a Bose-Einstein condensate that we then load into an optical lattice. So in order to understand the observables that I'm going to explain that we use to study the dynamics, it's enough to think about our system as a macroscopic wave function that is occupying the lowest energy eigenstate of the system. And then we are going to manipulate it and in some cases describe it in a semi-classical form. Now, these types of Hamiltonians, the Bose-Hubbard Hamiltonian, which is schematically drawn here for a square lattice, generally has a band structure that is topologically trivial. So in order to engineer something non-trivial, we have to add additional ingredients. And in our case, we use Floquet engineering or periodic driving, which in its basic essence means that we take one of our system's parameters or several of our system's parameters and vary them periodically in time. So what we do is we engineer a time-dependent Hamiltonian, h of t, that is periodic in time with this period capital T that is connected to the driving frequency. And then we can make use of Floquet's theorem and look at the stroboscopic dynamics of our system, which means that we look at integer multiples of the driving period when we probe the time evolution. So for one period of the drive, we can write down our time evolution operator and always express it in that form, where now here appears a new Hamiltonian HF that is time independent. And if we now probe the system at integer multiples of this driving period t, it's solely governed by this effective Floquet Hamiltonian HF. So this means that we can choose or engineer a suitable driving protocol in order to engineer various different Floquet Hamiltonians. And then depending on the driving protocol, it can have different properties. And the stroboscopic dynamics of our systems effectively mimics the properties of this Floquet Hamiltonian. And moreover, in the high frequency limit, in the high frequency driving limit, we can find, or we can write down a perturbative expansion of this Floquet Hamiltonian in powers of 1 over omega in order to have a nice analytic expression of the Floquet Hamiltonian, which then in the rotating wave approximation limit quite accurately describes the dynamics of our system. Now there's something that comes along with that, that is we now deal with quasi-energies that are only defined up to integer multiples of the driving energy quantum h bar omega. So if we compute the band structure of this effective time independent Hamiltonian, which could be such a cosine dispersion relation as depicted here, we have in the extended Floquet Brillouin zone scheme infinite copies of this dispersion relation. And in particular, if we now add interactions to this system, there can be scattering processes that goes out of one of these Floquet bands into higher Floquet bands. Okay, so we should keep in mind that there's this infinite series of copies of this band structure of the effective Floquet Hamiltonian. Now, this technique has been used to engineer especially two famous topological model Hamiltonians, which is the Hofstadter model that describes non-interacting particles in a square lattice in the presence of a homogeneous external magnetic field, which is here introduced by this complex hopping matrix elements between neighboring sites along the horizontal axis in this two-dimensional lattice, and along the perpendicular directions we have real hopping matrix elements. The second model that has been studied quite extensively now is the Haldane model, realized on a hexagonal lattice, where the topology arises due to complex next nearest neighbor hopping. And in contrast to the Hofstadter model here, the flux that is piercing one unit cell averages to 0. Now, both of these models have a very interesting energy spectrum, and in particular, very interesting topological phases. Now, what I would like to discuss here is a different limit. In the earlier works, periodic driving or Floquet engineering has been used in order to emulate the properties of static topological systems that do not naturally occur in the Bose-Hubbard Hamiltonian, as I tried to explain on the previous slides. That is, if we just prepare our atoms in a lattice, then the band structure is typically topologically trivial, but then we use techniques such as periodic driving in order to emulate quantum Hall systems, for example, and engineer the Hofstadter or the Haldane model. And moreover, in this high frequency limit, where this actually works very well, we have this well-known bulk edge correspondence, meaning that if we can know how to characterize the topological properties of the energy bands in our 2D systems, we also know what happens at the interface between two distinct topological phases. So by knowing all the Chern numbers of the energy bands that characterize the topological properties of the energy bands, we can also predict how many edge states occur at an interface. And here's just a small diagram of the transverse Hall resistance measured for quantum Hall systems, just to make this connection between what we can emulate in the high frequency limit with our systems. Now, the interesting question is what happens if we go away from this limit? And this happens if we now take this driving frequency to smaller and smaller values. So we go away from this limit where the driving frequency is the largest energy scale in the system, and where we can make this perturbative expansion that allows us to take the high frequency limit and apply the rotating wave approximation. So away from this high frequency limit, there can be interesting new topological regimes. And I've depicted this here in the lower right corner, where that depicts one of these interesting regimes that can occur. Here you see a two-band model where the bands are indicated as this blue and brown line. The topology of these bands is characterized by these integer valued Chern numbers, C+ and C-. And generally, we can predict the number of edge modes for a finite system by computing or well, the connection between the number of edge modes and the churn number is that we take the difference between edge modes leaving the band from the top and entering from below. So if you look at the small schematic diagram, you would say, well, this churn number for the blue band has to be equal to 0 because I have one edge mode for a finite system that leaves the band from the top and one edge mode that enters from below. And the same is true for the upper band. Again, I have an edge mode leaving the band from the top and entering from below. So the simple bulk edge correspondence that connects the bulk topological properties characterized by the churn numbers to the number of edge modes in a finite system would tell me that here the bands are actually topologically trivial. But somehow I still have topological edge modes in this system. And the reason for that is that in a periodically driven system, I have this quasi-energy spectrum where the quasi-energy is only defined up to integer multiples of the driving energy quantum h bar omega. So if I plot it in a reduced zone scheme, I can have an edge mode that is winding across my Floquet Brillouin zone. So it leaves the Floquet zone from the top, but this point is exactly equivalent to the one below. So the reason why we can have different or modified bulk edge correspondence in these periodically driven systems is that we have this quasi-energy spectrum where we have no notion of a true lowest energy band in the system. And this is interesting because it gives rise to new phenomena that have been predicted. For instance, that in these systems, even if all the bulk states are completely localized, we can still have a topological edge mode in the system because it's determined by this non-trivial winding of the energy spectrum. And a nice intuitive way to understand how these non-trivial properties arise is, or can be explained using the stepwise modulated square lattice, which is one of the earliest models that has been introduced to study these types of physics. So this model is very simple and it's a fine-tuned example, but it illustrates nicely the properties of these anomalous Floquet phases. Assume that we have a bipartite square lattice where we can control the hopping along these colored bonds very precisely. And now we imagine that we have a four-step protocol where we turn on tunneling only along these colored bonds and we fine-tune it in a way that it corresponds to exactly one tunneling event. So if we prepare a wave packet on this black side and switch on tunneling for this quarter period of the driving protocol, the wave packet tunnels over exactly to the white side during this one step of the modulation protocol. If I follow this along these four steps and turn on tunneling only along the colored bonds, I will find that after one driving period, the wave packet has reached or traveled to its original position precisely. So meaning that if I now write down the Floquet time evolution of my system or the stroboscopic time evolution of my system after one driving period, it's the identity operation and the effective Floquet Hamiltonian is expected to be trivial. So why does this system still give rise to interesting physics? The reason is that if we now look at the edges of this system and prepare a wave packet there, we will see that it can only travel exactly along one direction. So if I prepare a wave packet in a finite strip on the upper edge, it will travel to the left, while if I prepare it on the lower edge, it will travel to the right. And this, as you can see by following this modulation protocol, is somehow encoded into what happens within one driving period, what we call the micromotion. So it's important to follow the complete time evolution of the system, even at times within one driving period, in order to understand the non-trivial properties. And moreover, if we now define this modified bulk edge correspondence and try to characterize the topological properties of these driven systems, we can define new topological invariants that will be defined precisely by taking into account the full time dependence of the evolution operator. Okay, so how can we actually do that? These topological systems are actually characterized not only by the churn numbers of characterizing the bulk energy bands, but by also computing the winding numbers that characterize the topological properties of the energy gaps and predict the number of edge modes in the gap. And what is important to note here is that the sum of these churn numbers for our models has to be equal to 0, meaning that actually if we only compute the Chern numbers of the system, for this two-band model, there's actually only one quantity characterizing the properties of the system. There are not two independent quantities, but if we then look at the winding numbers, those two numbers are actually independent quantities. So we get an additional information by computing the winding numbers of the gaps. And then again, they are connected. The difference between the winding numbers of the gaps above and below the band allow us to compute the Chern number characterizing the band. Okay, so if we are able to extract the winding numbers in the gaps, we have a complete set of invariants that characterize the topological properties of the driven system. So how do we do that in our experiment? In our experiment, we work with a periodically modulated honeycomb lattice. And similar to the square lattice that I have introduced before, we increase the tunneling amplitude along the colored bond. It's just that we don't go all the way to 0. The tunneling along the gray bonds is finite, but we increase it periodically in time. So we have this chiral modulation as a function of time. We first increase hopping along this red bond, then along that one, and then along the other one. And moreover, we apply a continuous modulation scheme, so we don't have a step protocol, but a continuous modulation, smooth modulation. And this can be implemented in our experiment by modulating the intensity of the 3 laser beams that generate the hexagonal lattice in the lab. So here's a plot of how we vary the intensity of each one of these 3 laser beams whose interference gives rise to this hexagonal lattice structure. Okay, and these are the phases that we find in our experiment as a function of the modulation frequency and the modulation amplitude. For very large modulation frequencies, we are in a regime that can be mapped onto the Haldane model that we know if we take the rotating wave approximation limit maps to static models. Now, if we decrease the modulation frequency, we enter the anomalous regime that I've just introduced before, where we have edge modes in the system, although the topological properties of the bulk energy bands appear to be trivial. And if we look at the spectrum for a finite strip, this is what actually happens. So here, this is a spectrum depicted for the Haldane regime, where the 2 bands have Chern numbers equal to plus and minus 1, and we have edge modes around 0 energy in this quasi-energy spectrum. Now, if we take the frequency to lower and lower values, we should think about having these Floquet copies approaching closer and closer together until there can be gap closing points between different Floquet zones. And this is precisely what happens. Due to a gap closing point between Floquet zones, we generate a new edge mode in this Floquet gap, while leaving the one at 0 intact. And this is the reason why now we have 2 edge modes in the system, one in each energy gap, and the Chern number of the bulk energy bands is equal to 0. And then if we take the frequency to smaller and smaller values, there will be several of these gap closing points. So we move these Floquet copies closer and closer to each other and generate a series of gap closing points. And here's another regime that we characterized in the experiment, where we have eliminated the edge mode around 0 energy, and there's an edge mode between Floquet baryon zones. So this is what we call a Haldane-like regime, because we again have Chern numbers equal to plus and minus 1, but now the edge mode is in this non-trivial Floquet gap, while there's no edge mode around 0 energy. Okay, so how can we actually probe that in experiments? First, we characterize the topological phase transitions by measuring the smallest energy gap in the spectrum and check where it vanishes. So we start in a high frequency limit and then follow the system along this white line through the parameter space and probe the energy difference, which is here depicted as these colored lines. The black lines correspond to a vanishing gap. And the way we do it is by using an interferometry sequence. I will not go into the details due to lack of time, but if you're interested, I can explain it in more detail. The idea is that we track the time evolution at a specific point in quasi-momentum space and then we find an oscillating behavior whose frequency is determined by the energy difference between the two bands. This is the experimental result. Following the white line through the parameter space, here we start in a high frequency limit. We measure the energy difference between the two bands. And then you see that there's a series of gap closing points. Here we probe exactly 2 of them, which allow us to identify the different regimes that I've introduced before. Now, you may ask what energy gap we are actually probing. So we have this interferometry sequence where we can measure energy gaps, but since we have this quasi-energy spectrum, there are various different energy differences that we could be able to probe with these techniques, the one specifically around 0 energy or the one between Floquet zones. Now, in our technique, it turns out that we always probe the smallest one of the 2, meaning that if we start in a high frequency limit where these Floquet copies are very far apart, we know that we are probing the energy difference between Floquet copies. Sorry, that we are probing the energy gap around 0 energy because that's the smaller one. So G pi is actually very, very large in a high frequency limit. G0 is the smaller one. But then if we tune this frequency to lower and lower values, we know that at some point they will become equal. And that happens precisely at h bar omega half because the sum of the 2 is always given by h bar omega. And then the notion of which energy gap we are measuring is actually changing and we switch to G pi. So we can actually identify which gap closing point we are probing with our experimental sequence. And the high frequency limit, we are probing the energy gap around 0 energy. Then at some point they become equal. That's the cusp in this data set. And then the notion which gap we are probing changes. We start to probe the gap between Floquet zones. And at this point, we know that the energy gap is closing between Floquet zones. While here at each cusp, the notion changes again. So we know that here in this white region, the gap around 0 energy is closing again. So this allows us to track in the spectrum where the gap closing point occurs, if it occurs between Floquet zones or if it occurs within a Floquet zone. Okay, so now how can we actually probe the topological properties of these bands? And there has been a number of methods in the past that has been developed to probe the topological properties of these Floquet engineered bands. And here I put the definition of the Chern number, which is defined as the integral over the barrel curvature over the Brillouin zone. And the barrel curvature is defined as the winding of the periodic Bloch functions, cell periodic Bloch functions, as a function of quasi-momentum Qx and Qy. So the topological properties are actually encoded in this geometric quantity, which is known as the barrel curvature. And we can extract it, or we can measure the values of the barrel curvature quite accurately by identifying the geometric properties of our eigenstates in the system. And one technique that has been used also in our lab is by interferometric measurements. And here the idea is that you load a Bose-Einstein condensate into the lowest eigenenergy state of your system. So it's some quasi-momentum, which typically is Qx and Qy equal to 0. And then you apply an interferometry sequence where you split the wave packet and let it travel along 2 different paths that you can combine at the end of your interferometry sequence. So the idea is to have a wave packet at the initial point and then split it and let it travel along 2 different paths to build an interferometry sequence. And the phase that you can extract at the end of the sequence is then directly related to the barrel curvature that is piercing the area of this interferometer, very similar to what you do in real space in an Aharonov-Bohm type interference experiment. Now there's another technique that we call state tomography, where the evolution of the eigenstate as a function of Qx and Qy can be mapped out directly in a 2-band model, which allows us to extract the barrel curvature locally for each quasi-momentum Qx and Qy within the Brillouin zone. So this is an example for a topologically trivial hexagonal lattice, where the Chern number of the band is equal to 0, and you see here regions of negative barrel curvature indicated as blue and positive barrel curvature indicated as red. And then the sum over all of these values would be equal to the Chern number of the band. And last but not least, Chern numbers or topological properties of energy bands have been now extracted from quench dynamics, and also machine learning algorithms have been applied in order to efficiently map out the full topological phase diagram, for instance, of the TopDyn model. This has been pioneered in a group of Klaus Sengstock and Christoph Weikenberg in Hamburg. Now, we have been using a technique that is more inspired from solid state physics, and we have extracted the Chern number from transport measurements. The idea is again to prepare a wave packet at a certain position in quasi-momentum space in a dispersion relation, and then apply a force to our atomic cloud that linearly changes the quasi-momentum as a function of time. And we probe, or we move the wave packet adiabatically through the band we are interested in probing. So what happens if we apply a force to our system is that the atoms undergo Bloch oscillation, and this velocity in the direction of the force is determined by the dispersion of the band. But in the presence of a non-zero Berry curvature, there's a transverse component to it, which we call anomalous transverse velocity or Hall velocity, which gives rise to a center of mass motion of the wave packet in real space that is perpendicular to the force that we apply to the system. And this transverse motion then allows us to extract the Chern number if we populate the complete band. So if we populate all quasi-momentum states at the same time, what we are measuring is essentially the integral over the full Berry curvature, which means we get a response that is proportional to the Chern number of the band. But we can also use it to probe the topological properties locally, and the idea is, so here I have plotted the Berry curvature of the lowest energy band in two different regimes, the TopDyn regime and the anomalous regime, which are characterized by Chern number 1 and Chern number 0. And the high symmetry points are indicated here as K and K prime. The central point is called the gamma point. So now if we take a wave packet that is concentrated in quasi-momentum space, we can move it across certain regions within the dispersion relation that are characterized by non-zero Berry curvatures. And then according to this formula that is given here for the anomalous transverse velocity, we can then measure the real space displacement of the cloud in order to characterize the Berry curvature that is concentrated at a certain position in quasi-momentum space. So we can use it as a local probe of the Berry curvature and map out the topological properties of the band. Okay, so now I have to speed up a bit. This measurement will actually allow us to track the changes in topological properties across the phase transition points. I mentioned now several times that we know precisely what happens in the high frequency limit. We know that the winding number between Floquet zones has to be trivial, and the winding number around zero energy is equal to 1. This is determined by the TopDyn regime, and we will now track the topological properties of the other phases by tracking how the winding number change in the different energy gaps, starting from this high frequency limit. And here's depicted one of these gap closing points in our 3D parameter space that is parametrized along this white line with this parameter lambda. And this gap closing point can be actually associated with a topological charge. We have a linear gap closing point, and the topological charge determines how the winding number changes across a topological phase transition point. So this is depicted here. It illustrates how the winding number changes, and the topological charge in our case is either plus or minus 1. And it turns out that, so I will skip that we can characterize the topological charge by measuring the Berry flux in a local regime in the dispersion relation just above and below the phase transition point as a function of this parameter lambda. And you can show mathematically that the Berry curvature actually changes sign. It flips from plus pi to minus pi across the phase transition point. So here the phase transition occurs at the gap closing point at gamma in the center of the Brillouin zone, and it changes from the Berry flux changes from plus pi to minus pi. So with our local deflection measurements, we probe the sign change of the Berry flux at the gap closing point. And this allows us to extract the topological charge of the gap closing point. So we have to know the topological charge and where it occurs. So between Floquet zones or around zero energy.
Sorry, Monica, we are out of time.
Yes, okay. So let me, since I already explained the technique, I can actually, I was muted briefly. I can skip that and just show you the experimental result where we probe the sign change. So you see the gap closing point actually occurs here always in the center of the Brownian zone. We measure a positive deflection of the cloud, which then when we approach the phase transition point, flips sign. So the deflection goes from going to the left to going to the right. And it allows us to extract the topological charge of the gap closing point. And therefore, since we also know where the gap closing point occurs, it allows us to extract how the winding number changes. And the same happens at the second phase transition point, where again, it flips from positive to negative. And since we know where the gap closing point occurs, we can extract the topological charge of the gap closing point, and we see how the winding number of here, the zero energy gap changes. So by doing this local deflection measurements, we can extract the complete set of topological invariants. And then with this, I'm actually at the end, and I would like to thank especially Karen and Christoph, who did all the nice measurements in the lab, and give you a brief outlook about what we are interested in doing in the future, looking at edge modes directly, probing the interplay with disorder. And with that, I would also like to on different topics, and thank you for your attention.